So I want to calculate the moment of inertia of the whole dumbbell about point A. So it's going to rotate like this into the page. I mean, on the page. All right, we obviously have a complex system that can be broken up into 3 subsystems. So this is the moment of inertia of the pulley about A plus moment of inertia of the rod about A plus moment of inertia of the solid sphere about A. 3 terms. 3 subsystem, 3 terms. Next, remember the next question is point A at the center of mass of my pulley? Is the answer yes or the answer no for the first term? No, excellent. Therefore, I have to use the Braggs's theorem. So this will be the moment of inertia of a pulley about its own center of mass plus the mass of the pulley, which is m1, times the translation factor delta 1 squared. Let's identify it later. Let's go to the next term and ask ourselves the same question. Is point A located at the center? Oh, excellent. Yes, point A is at the center of mass of the rod. Therefore, we don't have to use the Braggs's theorem. Excellent. Therefore, we can just use the result, I of the rod about its center of mass. That's the 112 guy. Perfect. Next term, solid sphere. Is point A located at the center of mass of the solid sphere, which we called C? Thank you, Tyson. Obviously not. Therefore, I have to use the Braggs's theorem. First, I will include the moment of inertia of the solid sphere about its own center of mass. That's a 2/5. And then I'm going to add the mass of the solid sphere, m2, times the translation factor, delta 2. Let's try to identify this burger. So, only 2 things we have to do. Identify theta, delta 1, and delta 2. By definition, delta 1 goes from the center of mass of your system, which is the pulley, all the way up to point A. And delta 2 will start at the center of mass of the solid sphere, all the way up to point A. So that means delta 1 is BA, and delta 2 is CA. Let's draw them so we don't make any mistakes. Then it's easy. Delta 1 obviously is L over 2 plus R1. And delta 2 is obviously R2 plus L over 2. Bing, bam, boom, done. Now let's plug. When we have a pulley about the center of mass, it's a pulley, therefore 1/2. Mass of the pulley, M1, radius of the pulley, R1 squared, plus mass of the pulley, and delta 1 is L over 2 plus R1. Everything is squared. Next term. We didn't have to use the Braggs's theorem because it was already at the center of mass. Therefore, it's 112. M3, length squared. And the last one, moment inertia of a solid sphere at the center of mass, is 2/5. Mass of the solid sphere, which was M2. Radius of the solid sphere, R2 squared, plus M2 times the translation factor theta delta 2, which is L over 2 plus R2 squared. Bang! 1, 2, 3, 4, 5 terms. Kilogram times meter squared. Done. Now we just plug numbers. Okay? Questions on this? Easy, huh? So read about the moment of inertia from the book. Again, there are very, very nice sections about it. And as you can see, the application of the Braggs's theorem is a piece of cake. Always ask yourself the following questions. How many subsystems can I consider? It's always going to be, for this particular class, one of 3 shapes: a rod, pulley, solid sphere. If you're calculating the moment of inertia about a point which is not located at the center of mass of any of those 3 subsystems, you apply the Braggs's theorem. If you're dealing with a 0-dimensional point, you don't have to apply the Braggs's theorem, even simpler. Oh, no. the units is kilogram times meter squared. Sorry. Let me put it here.